Okay.
Okay, good. So our next talk is by Yitong Yin from Nanjing University. Yitong is a professor in Nanjing, and yeah, his talk is titled Dynamic and Distributed Algorithms for Sampling from Gibbs Distributions. Okay, stage yours.
Okay, thanks, Han. Yeah, in this talk, I will survey some recent advances in dynamic and distributed algorithms for sampling. Okay, so we consider Gibbs distributions described by pairwise interactions. And in a graphical model, each vertex corresponds to a variable of q possible spin states. Every vertex v is associated with a local field bv, which is a function of q spins. And every edge e is associated with a symmetric function ae that describes the edge activities of q square possible interactions of spins. And each configuration assigns every vertex one of the q spins. And the Gibbs distribution is defined over all configurations, so that the measure of a configuration is proportional to this product of edge activities and local fields. And here, without loss of generality, we assume the edge activities are normalized to range between 0 and 1, and the local fields are normalized as distributions over q spins. Clearly, such normalization won't affect the definition of Gibbs distribution. And for this talk, we focus on pairwise interactions, although most of the results can be generalized to general interactions. Sampling from Gibbs distribution is a fundamental problem. Here we consider its dynamic version. Suppose that we have a sample X from the Gibbs distribution mu of the current graphical model. And the graphical model is updated to a new graphical model. Say some edges may be added or deleted, some edge activities or local fields may be changed. Here we assume that the vertex set V is always unchanged because adding and deleting independent variables are easy to implement. Now the dynamic sampling algorithm wants to modify the sample X of the current Gibbs distribution mu to a new sample X prime of the new Gibbs distribution mu prime of the updated graphical model. For example, given a sample of this async model on grid, when this edge is changed, we want to obtain a correct sample of the new async model by reshuffling only part of the sample, possibly close to the updated sites. We allow multiple vertices and edges to be updated. And so we measure the size of the update by the total number of vertices and edges on which the two graphic models differ, including those vertices and edges whose fields or activities have changed. We hope that the dynamic algorithm can edit the old sample to the new sample with small incremental cost, depending on the size of the update. And ideally, this incremental cost for the dynamic sampling should be near linear in the size of the update. So we actually want to establish a Lipschitz property for sampling from Gibbs distributions. When the input graphical model differ locally, the output samples should also differ locally. The problem is well motivated because graphical models nowadays can be very large, and it becomes quite wasteful to restart everything from scratch every time a small part of the graphical model has changed. And such dynamic version of sampling deviates a lot from traditional sampling techniques such as Markov chain Monte Carlo, and asks for some new ideas. And meanwhile, studies of dynamic sampling may contribute new ideas for sampling in the classic static setting. Good dynamic sampling algorithms.
Yeah. Interrupt. There's a question. Is the update cost in expectation?
Yes, we can measure the, yeah, in this talk we measure in expectation, but also there's a high probability version. Yeah.
Okay, thanks.
Good dynamic sampling algorithms can imply efficient algorithm for sampling from static input, because any static sampling problem can be interpreted as that we start from a trivial graphical model with no edges, which corresponds to a product distribution that is easy to sample. And then we update the graphical model by adding all edges back. A dynamic sampling algorithm with linear incremental cost implies a linear time algorithm for sampling from static input. Okay, so how can we sample dynamically? And how does a sampling algorithm have such Lipschitz behavior? Let's first see this Mossadegh style algorithm for dynamic sampling. Given a sample X from the current graphical model, Gibbs distribution, mu, when the graphical model is dynamically updated, the algorithm first constructs a set R of all vertices affected by the update. So for each vertex in R, either its local field is changed by the dynamic update, or it is incident to some edge that is added, deleted, or has its activity changed by the update. So basically, this R contains all variables that need to be fixed. While this R is not empty in each iteration, first, for all vertices in R, we resample their spins independently according to the local field. And then every edge incident to these resampled vertices, no matter whether having both vertices resampled, thus are an internal edge, or having just the one vertex resampled, thus a boundary edge. No matter in which case, every such edge needs to recheck whether to locally accept or reject the new sample by flipping a biased coin. And finally, all vertices and the rejecting edges form the new set R. Morally, this is a Mossadegh algorithm. The violating variables are resampled and the local constraints affected by the resampling are rechecked. But here, the constraints may be soft constraints. And for the internal edges in R, the acceptance probability is just the edge activity, which is aligned with the definition of Gibbs distribution. But the boundary edges are handled separately. For each boundary edge, the acceptance probability is proportional to this ratio between activities after and before resampling. This minimum is just a normalizing factor computed from inside the set R to ensure this ratio is always a probability. Okay. And this algorithm reminds us that the Gibbs distribution can be generated by this natural rejection sampling procedure. Every vertex spin is sampled according to the local field. And every edge locally accepts the sample with probability of its edge activity.
Another question. So Christopher asked, the set R could grow?
Yes, yeah, it could at some times. But we wish it will vanish, yeah, in the end.
Okay, thanks.
Yeah. So yeah, this classic rejection sampling generates the Gibbs distribution. So conditioning on conditioning on that all edges accepts the sample is distributed precisely at the Gibbs distribution, although the probability of being accepted by all edges may be exponentially small. Oh, okay, back to this Mossadegh style dynamic sampling algorithm. The philosophy is that when part of the sample is incorrect, no matter due to rejection or due to the dynamic changes of the underlying graphical model, we do not restart the entire rejection sampling procedure, but instead we try to fix the incorrect part by resampling. The separate handling of boundary constraints is necessary for ensuring the correctness of sampling. the upward distribution. And this algorithmic framework was introduced by the partial rejection sampling for uniform solutions of Boolean CSPs. Okay, that's our Mosotadish style dynamic sampling algorithm. And before talking about its analysis, let's see another dynamic sampling algorithm. It is a hit bus-based algorithm. Initially, we still have the current sample X, and construct a set R of vertices affected by the dynamic update of the graphic model. Now we try to fix one vertex, one incorrect vertex U at a time. Hopefully just by resampling its spin according to its current marginal distribution. And this is the well-known hit bus translation in the so-called Glauber dynamics or Gibbs sampling. But trying to fix vertex by just this hit bus resampling will cause a bias. So we use a filter before resampling to cancel this bias. With probability inversely proportional to the current marginal probability of U, the filter succeeds and we apply the hit bus translation and successfully fix U. Otherwise, the filter fails and we add all neighbors of U into R. So in this branch, R grows. Yeah. Here, this proportional means this proportional relation still means that we choose a proper normalizing factor to make sure this ratio always a probability. You can imagine that the normalizing factor is just a minimum possible value of this marginal probability in the denominator, where the minimum is estimated from inside R. And this is our second algorithm. It's just the hit bus translation corrected by a filter inversely proportional to the current marginal probability. Sorry, I don't quite understand the problem, the question. Okay, it passed. Okay, so now let me explain how these two dynamic sampling algorithms are correct. Both algorithms maintain an XR pair, where X is the current sample, a random configuration, and R is the set of currently incorrect vertices. The algorithms are Markov chains on pairs, but the purpose here is not mixing, but hitting. The chain stops when R is empty and the current sample X is returned. So the sampling algorithms are Las Vegas. They know when to stop. The crucial invariant here is this so-called conditional Gibbs property. It basically says that conditioning on any set R of incorrect vertices and the configuration on it, the rest of the sample follows correct marginal distribution induced by the Gibbs distribution with the current configuration on the incorrect part as boundary condition. And with this property holding as an invariant, when R is empty, the current sample X follows precisely the Gibbs distribution. So if this conditional Gibbs property holds as an invariant, the algorithms are perfect samplers with no errors. Formally, this invariant can be expressed as linear system. The translation of the chain linearly transforms the marginal distribution on the currently correct part of the sample to that in the next step, up to some constant. And both the Mosotadish dynamic sampler and the hit bus dynamic sampler are solutions to this linear system. So they both satisfy this invariant and the correct as dynamic samplers. And as we mentioned earlier, if initially we start with R equals V, the set of all vertices, these algorithms become perfect samplers on static input. And furthermore, the conditional Gibbs property guarantees that these perfect samplers on static inputs are interruptible. It means that if we run this algorithm in some experiment, if the algorithm has run for too long, we can simply stop it and restart. It will not bias the final output. Such property was rare in previous perfect sampling algorithms, especially the ones based on coupling from the past. And some previous perfect sampling techniques also satisfy this conditional Gibbs property retrospectively. So now let's take this heat bus dynamic sampler as an example. Let me further explain how this particular algorithm satisfies this invariant of Gibbs, a conditional Gibbs property. First, for the success branch of the filter, the new set R prime successfully fixed the vertex U, or successfully removed U from out of R. Then, due to the conditional Gibbs property for the current step, we have that the good part of the configuration, this XR bar, distributed correctly. But our goal is to have XR bar distributed like this in below. Here it is R prime, and up here it is R. The only difference between R and R prime is this vertex U. R prime does not have vertex U. This one in below is our goal, because if we have this, then resampling the spin of U from its marginal distribution will extend this XR bar by one vertex U, becoming an R prime bar. And by a simple chain rule, it must be distributed correctly, satisfying the invariant of conditional Gibbs property for the next step. So in order to transform this marginal distribution above provided by the invariant for the current step to this one below, which implies the invariant for the next step, we introduce a filter that succeeds with probability proportional to this ratio between these two marginal probabilities. Here it is the R prime. Calculated by the Bayes theorem, it is proportional, inversely proportional to this marginal probability. Here the numerator depends only on the XR, which is fixed as a boundary condition in the beginning by the conditional Gibbs property. So it can be treated as part of the normalizing constant. This gives us exactly the filter in the algorithm. And for the failure branch that's for the success branch. And for the failure branch of the filter, we simply include all vertices in the algorithm has just observed into the set R. So the conditional Gibbs property holds trivially for the next step, because the algorithm has put everything it has been conditioned on into its boundary condition. Overall, the conditional Gibbs property holds invariantly for this simple algorithm. Recall that the heat bus transition is perhaps the most canonical strategy for MCMC sampling. And it's somehow surprising to see that it can be turned into a dynamic and Las Vegas perfect sampler by this simple filter. And that's for correctness. The efficiency of the algorithms is bounded by establishing a stepwise decay of the set R or some suitable potential denoted abstractly by H here. This is a quite standard way for bound the convergence rate for such algorithms. In particular, for the most tightest dynamic sampler on graphs with bounded maximum degree, when the edge activities are always close to 1 like this, the dynamic sampler is efficient with the linear incremental cost, linear in the size of the update. And if applied for static sampling, it gives us a linear time perfect sampler on static input. For specific models, such as Ising and hardcore models, the same efficiency is achieved in regimes in the interior of the uniqueness regimes. and are close to the critical threshold up to some constant factor. And I want to further comment that such stepwise decay argument is not as sophisticated as the Mossadegh style analysis, like forward and backward analysis or entropy method. And adopting the more sophisticated analysis in sampling will be very interesting. And that's for the Mossadegh style dynamic sampler. On the other hand, for the heat bus dynamic sampler, we consider a block version of the sampler, where the heat bus transition as well as this filter are defined on blocks of a sufficiently large constant radius. On graphs with sub-exponential neighborhood growth, a decay of correlation property, namely the strong spatial mixing, implies dynamic sampling with linear incremental cost. The strong spatial mixing says that the boundary to vertex influence decays exponentially as the distance between the vertex and the disagreeing boundary grows. On graphs of sub-exponential growth, this decay of correlation property guarantees that the blocked heat bus dynamic sampler converges very fast. And consequently, it implies a linear time perfect sampler on static input. Recall the well-known equivalence between spatial mixing and the rapid mixing on graphs with sub-exponential growth. We now can lift either the strong spatial mixing or the rapid mixing of block dynamics to the efficient dynamic sampling or perfect sampling on such families of graphs. And also very recently, there is an alternative data structure approach for dynamic sampling. Say we have a trajectory for single site dynamics, which is long enough so that the chain mixes. We express the Gibbs distribution in this Hamiltonian form. And when the graphical model is updated, we now measure the size of the update by this L1 distance between Hamiltonians of the new and old graphical models. So now we allow such global updates that all edge and the vertex Hamiltonians are changed simultaneously, but maybe by a small total amount, like constant. Such global updates are common in iterative inference algorithms such as the stochastic gradient descent. And we found that assuming the Dobryshin's condition for path coupling, the trajectory can be modified to a new trajectory of single site dynamics for the new graphical model, so that the steps at which the two dynamics use different random choices are very rare. This is the Lipschitz property for single site dynamics implied by path coupling. Consequently, there is an efficient dynamic data structure for MC sampling compared with the previous two dynamic sampling algorithms based on conditional Gibbs property. The data structure approach is for approximate sampling and also has some overhead in space cost because it has to store the trajectory of the dynamics. So the conditional Gibbs property implies space efficient dynamic sampling and also interruptible perfect sampling. It is a good property. But we are still not sure whether the conditional property is strictly stronger than the phase transition property for Gibbs distributions, such as decay of correlation. Because it indeed can support some seemingly stronger algorithms. We know it is not on graphs with bounded growth. It will be very interesting to see whether this is true on general graphs, especially highly expanding graphs. And another caveat is that in dynamic sampling, the current sample and the new sample can be highly correlated because they can be the same almost everywhere. However, morally, this should be fine, at least for applications like computing marginal probabilities. Because intuitively, far apart spins don't matter due to decay of correlation. And meanwhile, the nearby spins have much higher chance to be resampled, thus break the correlation between samples. This is not rigorous. Rigorous analysis of the impact of correlations between samples in dynamic sampling is quite interesting and should be done in the context of specific applications of sampling. Okay, that's all for the dynamic sampling. For the next maybe 12 minutes, let me talk about distributed Gibbs sampling. Distributed Gibbs sampling. Consider this Mosatadis style sampler. As we said, if we start by setting the set R to be the set V of all vertices, this algorithm becomes a perfect sampler on static input. And this Mosatadis style algorithm can be executed in parallel. And the situation here is much simpler than the original parallel version of Mosatadis algorithm for the local lemma, because here we don't need to construct a maximal independent set. We just resampled all violating variables simultaneously and independently. And this algorithm is clearly easy to implement in a message passing model by distributed algorithms. And by the same stepwise decay argument within the same regimes, this distributed algorithm on static input terminates in log and round. So it gives us a log and round distributed algorithm. So how good is this log and round complexity? And can we do better in complexity or in regimes? Now, formally, let's see, for distributed sampling problem, we assume that the underlying graph of the graphical model is also the network for the distributed algorithm. And we assume a standard message passing model. Upon termination of the distributed algorithm, a random configuration X is returned, with each vertex outputting its own spin. And for perfect sampling, we require that the output configuration X is distributed as precisely as the Gibbs distribution mu of the input graphical model. And for approximate sampling, we require X to be close enough to the Gibbs distribution mu in total variation distance. And an unconditional lower bound says that log and rounds are necessary even for approximate sampling with constant error. And that holds for any non-trivial Gibbs distribution due to the correlation in such distributions. So log and round upper bound is optimal for distributed Gibbs sampling. So can we do better in regimes? Let's recall the canonical method for sampling, the MCMC method. In a single site dynamics, at each step, a random vertex is picked and its spin is updated according to the current neighborhood configuration. The optimal mixing time for such chains is n log n steps. Therefore, to obtain an optimal log and round parallel and distributed sampler out of this classic single site Markov chain, our deal is to fully parallelize the single site dynamics with ideal speed up factor n. However, because the update of a variable depends on neighborhood configuration, concurrent updates of two adjacent variables cause a race condition, where the two adjacent vertices' knowledges about each other's current spins are outdated by the concurrent updates. And this will cause a bias to the sampling. A natural way to avoid this is to use a chromatic scheduler so that no adjacent variables are updated in the same round. But this will introduce a max degree overhead in the parallel speed up, because in each round, within every neighborhood, at most one variable can be updated. Alternatively, in the so-called hog-wild approach in the practice of machine learning, every vertex just obliviously executes the same code as in the original single site dynamics, ignoring the concurrency. This strategy will clearly bias the sampling in the worst case, but assuming independently random delays of messages, it can be good enough for certain tasks. So now the question is, can we parallelize the sequential chain with both optimal speed up and no bias in sampling? There is indeed a parallel version of the Metropolis chain that can do this. Here is a well-known single-site Metropolis chain for Gibbs sampling. At each step, a randomly picked vertex V proposes a random spin CV according to its local field and accepts the change with probability, this product of local factors. The parallel variant of this chain is like this. At each round, every vertex V independently proposes a random spin CV according to the local field. Then every edge UV accepts independently with probability of this product of 3 possible interactions between the current and proposed spins of the 2 endpoints. At last, each vertex accepts the change if all its incident edges accepted. And now we cannot simply write the acceptance probability as above in the product form at vertices, because now adjacent vertices share randomness through the edge between them. And that's crucial for the correctness of this parallel chain. And this parallel chain is correct in stationary, and it mixes in log-n rounds. Actually, it's lazy version that mixes in log-n rounds under the same path coupling condition for sequential Metropolis chain. So it successfully parallelizes the mixing sequential Metropolis chain as long as the mixing is due to path coupling. And this parallel chain circumvents the max degree barrier, because in every round there is a constant fraction of vertices successfully updated in expectation, no matter how large the max degree is or even unbounded. And also this algorithm has been applied in the local computation model. So we have designed a brand new parallel Markov chain for sampling. But recall that the single-site Markov chains were actually born parallel. Recall that the continuous time chain, where every vertex holds an independent rate 1 Poisson clock. When the clock rings, that vertex does the single-site update atomically. The discrete single-site dynamics we see today is actually a discretization of this continuous chain, with continuous time t corresponds to nt discrete steps. So if we can faithfully simulate continuous time t in discrete OT rounds by a distributed algorithm, we win. But this can be complicated because of discrete time and non-atomic executions. To resolve an update at a vertex, a naive way is to wait for the up-to-date information about the neighborhood configuration. But this will meet the same max degree barrier because concurrent adjacent updates are not allowed. A new idea here is to resolve single-site update in advance. This new idea applies for Metropolis chains. Abstractly, for any Metropolis chain, when the Poisson clock rings at a vertex, the vertex proposes a random spin and flips a bias coin to decide whether to accept the proposed spin, where the bias of the coin is determined by the current neighborhood configuration as well as the proposal. We can assume that the Poisson clock's ringing times and proposals are locally generated by every vertex and exchanged among neighborhoods, which takes only 1 round. And now to resolve a proposal at vertex V at time t, we need to flip this biased this biased coin. Ideally, if the neighborhood configuration at time t is fully known, this bias is known, and we can flip this coin correctly. The main idea here is to correctly flip a coin before its bias is fully known. For example, suppose that to resolve its own update, vertex V needs to know the neighbor's U's spin at time t, but U has only progressed up to this time, this blue line. But V wants to know the spin of U at time t, at this red line. So the correct spin of U at time t is not known to V, but that spin must be among the current spin of U and also the proposals between these two lines. And that's due to the definition of a Metropolis algorithm. So even when the precise neighborhood configuration at time t is not fully known, we can construct a set of possible neighborhood configurations at time t and estimate the upper and lower bounds of this bias. So the main task here is to flip a biased coin as early as possible. Meanwhile, the upper and lower bounds of this bias become more and more accurate as time goes by. And this can be achieved by simply by sampling a uniform real number from the interval between 0 and 1, and maintaining the dynamically changing upper and lower bounds of bias within this interval. As more information received by the vertex V, these upper and lower bounds are getting closer and closer to each other. The coin flip is successfully executed once the random real number lies above this upper bound or below this lower bound. So this is a smarter than naive strategy for distributed simulating the Metropolis chain, although the analysis is much involved. Anyway, this simple idea parallelizes any Metropolis chain with optimal speed up under fairly moderate condition. For these typical graphic models, the optimal parallelization is achieved in regimes much bigger, much broader than the uniqueness regimes. This is not contradictory because here our goal is to faithfully simulate the chain, no matter whether the chain itself is rapidly mixing or not. And the current approach crucially relies on Metropolis chain, where each transition is a coin flipping. It's a very interesting open problem to have faithful and optimal parallelization of general single-site dynamics. Okay, so to summarize, there are quite some new ideas for dynamic sampling and distributed sampling. There are also some open problems like have algorithms satisfying conditional Gibbs property approach the phase transition thresholds on general graphs and control the impact of correlation in samples in dynamic sampling, and also parallelize the general single-site dynamics, for example, the Glauber dynamics, and especially apply the new ideas here to improve sampling in classic setting, like using Mosotadish style tight analysis for sampling. And thank you all for your attention.
Thanks, Yitong. We're very grateful to have Yitong today because actually right now it's already past midnight in China. Okay, I still don't see any question yet. Okay, maybe I will start with a question. The same question I asked quickly. So do you think there's a distributed and dynamic algorithm, sampling algorithm for matchings without degree bound? I know there are some ways for bounded degree.
That's a great question. Yeah, for bounded degree, you said, yeah, probably there is, but for unbound degree, yeah, unbound degree matching.
What's your guess?
I guess there's no distributed, and there's no even parallel algorithm for in polylog rounds for matching in general graph. That's my guess. And for dynamic It really depends because it can be made dynamics, but the incremental cost is bad. So, yeah, it depends on how do you define the dynamic algorithm. Do you want polylog incremental cost? Then I think that's difficult. That's hard, probably impossible. But if you can tolerate incremental cost smaller than the cost for sampling itself, then probably there is. Yeah, that's my answer.
Okay, thank you. Yeah, maybe I will squeeze in another question. So Yuanjia asked, yeah, in dynamic sampling, if the perturbation of the AE is global, of the basic edge weights, I guess, is global, is it okay to just separate it into local changes, or do we need a different algorithm?
Yeah, we need a different algorithm because I mean, I assume that global means you can change all edge activities, but by a small total amount. So that we can only do that by data structure approach, but not by the perfect dynamic sampler, by the conditional Gibbs property. So yeah, that's a different algorithm. It does not work like separated into local changes.
Okay, thank you.
Okay.
All right, so we'll have a short break.